So we have a beam like this, which is having supports at A and C, and CD is overhanging part, and it is acted upon by three loads, one UDL, one point load, and one uniformly varying load. So first step is, as usual, the calculations of reactions. So before calculating reactions, I have converted this uniformly varying load to the point load by determining the area of this triangular load. So that will be half into 18 into 3, right? So, and this load will act at the CG of this triangle, that is at 1 meter from A, because the CG is h by 3. Now we calculate the reactions using equations of equilibrium. Okay, so I have already calculated the reactions. Now the next part is calculation of shear forces. So VA we calculated 25.6 and VC is 19.4 kilonewton each, and we have converted this load to a concentrated load of 27 acting at 1 meter distance. So now for calculating the shear forces, I will start from A towards D. So first section I will take the left of A. Okay, so this is my first section. So shear force at A will be, because VA is the only upward force on the left hand side of this section, so, and we are using this sign to be, this direction to be positive and this direction to be negative. So as we have a upward force on left hand side, then we will take it to be positive. Then we will calculate shear force at B. So as I have told you earlier, we will take two sections, one at the left and another at the right hand side of B. Okay, so this is section 2, this is section 3. So when I look at section 2 at the left hand side of section 2, then we have two forces. One is this VA and another is this 27 kilonewton load. So plus 25.6, and this downward force is taken negative, so minus 27. So we will get 1.4 kilonewton. Next, shear force at B. So okay, so this was at left and now at right. So I'm taking section 3. So looking at the left hand side of section 3, we have three forces, 25.6, 27, and now this 10 kilonewton force also. So 25.6 minus 27 plus again minus, because this is downward. So we will get minus 11.4 kilonewton. Similarly, I will take shear force at left of C and shear force at right of C. So left of C section 4, right of C section 5. So at the left hand side of C, if we look at the left hand side of section number 4, we have these three forces plus additional UDL of 2 kilonewton. So this is the UDL acting on the right hand side of C, and it is acting, so on the left hand side of C, and it is acting up to a length of 2 meter. So 25.6 minus 27 minus 10 and minus 2 into 2, because this is a UDL acting on 2 meter length. So we will get minus 15.4 kilonewton. Then on the right hand side of, we will do the calculation right hand side. So I will just write minus 15.4 plus 19.4. So 4 kilonewton. Now to calculate shear force at D, I will take a section at just left hand side. So this is section number 6. So shear force at D will be now all the previous loads, plus if we look at the left hand side of section 6, apart from these previous loads, another load is acting, which is this UDL acting on CD portion of 2 meter length. So I can write 4 minus 2 into 2 because UDL is 2 acting at 2 meter. So we will get shear force at D to be 0. So these are all the shear forces which we have calculated. Now we go to the third step, which is calculation of bending moments. I will again mark these loads. Okay, so as we know, this is a beam having simple support at A. So I can write that MA will be 0, and I can also write that MD is equal to 0 because D is at end of overhang. Okay, and A is our hinge support or simple support. So here also moment will be 0. So we will calculate moment at B and C. So for calculation of moment at B, I will take this section just at the left and of B and look on the its left hand side. So we will get the moments as 25.6 into 3. So the moment due to this VA, which is reaction 25.6 at B point, is 25.6 into 3, and we are taking these sign convention to be positive and negative like this. So this is a clockwise moment, so clockwise on left hand side is taken positive. Minus 27 into 2 because this is will be anti-clockwise, so we will get 22, so positive 22.8 kilonewton meter. Then bending moment at C. So for calculating bending moment at C, I will take section here just at the right. I am not taking section at the left, I am just taking at the right. You can calculate by considering left this section also. It is up to you, right? But for now I am not doing that because this calculation will be easier and smaller for me. So the bending moment will be only due to this UDL. So 2 into 2 into 1. And this bending moment will be clockwise. And now we are looking on the right hand side of the section. So if on the right hand side of the section the moment is clockwise, we take the sign to be negative. So that's why I put here negative sign. So this will be minus 4 kilonewton meter, right? You can also calculate the same by taking section here, and you will and considering all these forces, that is this 25.6, 27 and 10 kilonewton forces, and you will get the same value, right? So these are the different values of bending moments. Now we will plot the shear force and bending moment diagram. So I have written here the different values which we have obtained. So the shear force at A is positive 25.6. Shear force at B has two values, minus 1.4 and minus 11.4. So below B I will draw one value 1.4 and another value 11.4, both on the downward hand side. Then at C we have two values again, minus 15.4 and then positive 4, so upward, right? And at D we have 0. Now we will join these. So now between A and B we have a uniformly varying load, and for uniformly varying load the shear force values are connected with the help of a parabolic curve. So we will join the shear force at B on the left hand side, which is minus 1.4 and 25.6, with the help of a such, I will draw against parabolic curve, right? Then from minus 1.4 the shear force goes to minus 11.4, minus 11.4. Then at C point it goes to 115.4, and between B and C we have UDL, therefore we will join with an inclined line. Then from minus 15.4 it goes to positive 4, then it goes to 0, and again inclined line due to UDL load. So this will be the shear force diagram. Now for bending moment diagram, the value at A is 0, value at B is 22.8, which is positive. So here we have 22.8. Then at C it is minus 4, and at D it is 0, right? So from 0 to this 22.8, that is below this point B, we have UVL. So bending moment values will be joined with the help of a cubic curve, right? So something like this. So this is cubic in nature, right? Then it goes to 4, and we have a UDL. So for UDL we have so it will curve, so it will be this. Okay, so this is parabolic, and then we have a UDL again. So again it will be parabolic. So this is the bending moment diagram which we have obtained. But still, uh, what the problem is here, that we don't know where will be the maximum bending moment. We have not determined the value of maximum bending moment, right? So we know from previous concepts that bending moment will be maximum where shear force is 0 or where shear force changes sign. So if you look at the shear force diagram, you can see this is the point where the shear force is 0. So corresponding to this, the bending moment should be maximum. So this means that I have plotted this value, I have plotted here 22.8 to be maximum. So this is wrong. So I will delete this part for now, right? So this means that this value is not correct. We have to determine the value at this location, which is, if I draw it, this section. So this line, mark this with another, push it from the rest of my, so this was the B point, right? This line is representing B. Now I am drawing the section where bending moment is 0. So at this section the bending moment is 0. Okay, so this was 11.4 shear force, right? So what we need to do is, we know from our experience that, and we know from the basic concepts that bending moment will be maximum here, right? So below at point B the bending moment was 22.8, so the maximum bending moment will be somewhere above it, somewhere here, right? We don't know the value at, but we know that it will be at this section. So first of all, again, like we did in one previous question, we have to find out the location of this section, right? And then we will calculate the value of bending moment at this section, right? But the problem here in this question is that if you look at the shear force diagram, this shear force diagram is parabolic in shape from A to B because there is a uniformly varying load. So we cannot apply the similar triangles theorem in this shear force diagram, right? So we will have to use some another method to find this value. So what we will do is to locate this point, I will locate it in this loading diagram first, right? So let us say that in our this beam, this point having maximum zero shear force or maximum bending moment is at a distance of x from A, right? So first what we will do is we will consider this loading diagram and then we will solve, right? So the next step is calculation of maximum bending moment. So for that, this is my UVL acting on AB length, right? And this is my section where shear force is 0. Okay, so let me draw the shear force diagram again. So it was something like this, and this is parabolic. Okay, so this is the loading diagram of UVL and this is the shear force diagram. Okay, and this value is 18 kilonewton meter per meter, right, per meter, and we have assumed this distance to be x, so the remaining this will be 3 minus x because AB is 3 meter long, right? So we will consider this this is the loading diagram, right? So in the loading diagram or in the beam, let shear force is 0 at a distance of x meter from point A, right? So if W is at this section, so if here at B at load is 0, UVL is 0. This section let us consider it is small w, and at this section this is 18, right? So from the similar triangles in these two triangles, we will have 3 minus x upon w is equal to x is equal to 3 upon 18 because the length of the bigger triangle is 3 meter. So 3 upon 18. So from this we can find out W as 6 into x minus 3. So this means value of the load at this section, that is where the shear force is 0, is W into 6 into x minus 3. Right? Oh sorry, not x plus 3 minus x. Okay. Now we know that shear force at this section is 0. So we will write the equation for shear force at this section. So that will be, so here we have a reaction 25.6. So 25.6 minus the triangular load or the UVL at this section will be half into W into 3 minus x, because the we have to convert UVL into point load, so I have converted by taking the area of this triangle. So this is W, this is 3 minus x, so half W 3 minus x, and this shear force is 0. This we know, right? So now I will substitute the value of W here. So 25.6 minus half into 6 into 3 minus x into 3 minus x is equal to 0. So when we solve this equation, we will get a quadratic equation because we will have x square. So after solving, we are getting x as 2.317 meter from point A. So this means shear force is 0 and bending moment is maximum at a point 2.317 meter A. So now I know the distance of this point, so I can say that x is equal to 2.317. So I can calculate the maximum moment at x is equal to 2.317. So that will be 25.6 into 2.317 minus 27 into 3 minus 2.317, right? And this we are getting as 23.76 kilonewton meter. Okay, so how I have calculated this, I have I want to know the bending moment at this, which is this point. X is equal to 2.317, right? And this load is acting 27 kilonewton. So sorry, this will be, I have written here wrong. It will be 2.317 minus 1, because this distance is 1 and this is 2.317, so we will have 1.317 as the distance. So this is 23.76. So again we will go to the bending moment diagram, and now I can mark this value as 23.76 and this was 22.28, and then we will join it with the cubic curve, because here we have a UVL and here we have a UDL, so parabolic curve. Okay, so this will be the bending moment diagram. Okay, for this